We've seen how convolution filters on graphs are defined with coefficients h, but now of course we want to learn these graph filters. We want to learn the coefficients of these graph filters, and we want to stack these graph filters into larger networks. As in a multi-layer perceptron, we want to stack also multiple affine transformations together with nonlinearities into multiple layers. But now let's first look at a single graph filter. In that sense, a single linear layer equivalent in a multi-layer perceptron, and see how we can learn the filters. Let calligraphic D denote a data set of input and output signals on the graph, as well as the graph representation itself. So this data set is composed of triplets, xi, yi, and si. Potentially, this dataset could contain elements from different graphs, and we could train a graph filter that is becoming robust to different graph representations. As long as in the test set we're seeing graphs from the same distribution, despite these graphs being not the same, we can still process them with such a graph neural network, because S is known for both the training and the test graph, and the neural net, or the graph filter in this case, has learned to work well on the whole distribution of graphs. This is the beauty of graph neural networks. You can train graph neural networks on a set of graphs and apply them on a different graph, which is of course not possible if we would just have a multi-layer perceptron on the vertices defined. So now let fh of input signal x and graph shift operator s denote a graph filter, which means in the notation that we've used in previous lectures, y hat, the prediction, this is the output, the predicted output of this graph filter, is fh of x and s, which is just this polynomial of the graph shift operator to the power of k and x with coefficients h, k, which are now the parameters of this model. That's why we indicated them here as a subscript of the function f. During training, we now seek to minimize a loss function, as we usually do in empirical risk minimization, where we try to find h star as the minimizer of this objective, which is simply the sum over the entire data set of some loss function that compares the prediction of the model, the signal y hat predicted by the model, to the true output signal. And this optimization, this is important, is only over the filter coefficients. The inputs x and the outputs y, and also the graphs, the graph representation in form of the graph shift operator, are provided as prior information. Now, in some cases, we might not be interested in inferring signals that have the same shape, output signals that have the same shape as the input signals. In this case, when the output y is of a different dimensionality than the input signal, or is not a graph signal, then we simply add a readout layer to this model. And we'll do this also for models, for deeper models that we'll look at in a bit. So we have used n as the number of vertices or nodes in the graph, which means the input signal is an n-dimensional vector. Now we assume that the output is an m-dimensional vector where m is not equal to n. So we can of course take the prediction of this graph filter, which is n-dimensional, and multiply it with a m times n-dimensional matrix R, so-called readout matrix R, for matching dimensions. And typically, R is not learned, but is a design choice of the algorithm or the algorithm designer. So typical examples for the readout layers include, if we want to read out just a value at a single node, then this readout corresponds just to a unit vector where the 1 is at the corresponding component that we want to read out. If we want to read out a summation over, like we want to do an average pooling or a sum pooling over all the elements of the graph signal, over all the n elements, then we can just take the 1 vector, the transposed 1 vector, and multiply it with the output here in order just to take the sum over all the elements, etc., etc. So readout layer is used in order to produce outputs that are different, of different dimensionality than the dimensionality n of the input graph signal. And for instance, a summation readout would be useful in order to tackle classification problems where the input is a graph and a graph signal and the output is a particular category. Okay, so this was about learning a graph filter, which you can think of as a single layer graph network. However, one thing is missing, and that leads us to graph convolutional networks, or one step closer to graph convolutional networks, which are graph perceptrons. They are also single layer graph networks, but they combine the graph filter that we've seen before with a nonlinearity G that could be a pointwise sigmoid, tanh, or Rayleigh, just as we applied them in the context of multi-layer perceptrons. By adding such a nonlinearity, we go one step closer to making our model more expressive. The model before could only learn linear maps. We just had a convex combination of these graph shift operators with x and then h with this power series. So everything is linear. Now with a nonlinearity on top of this, we can learn mappings that are slightly more expressive, that are at least nonlinear. So it captures a larger function class. It's the equivalent to the perceptron of neural networks. To define and it's the first model that could, if you would use a sigmoid here, that could basically do classification. To define a graph convolutional network now, we take these perceptrons and, as in an MLP, recursively compose these perceptrons, these graph perceptrons in this case, into layers. So we have a graph perceptron here where the h has an additional index L for the layer, and x has now an index for the layer as well. So we take the signal from the previous layer, we multiply it with s to the power of k, and then with this scalar coefficient HLK, the coefficient at layer L, and for that particular k here. And then we apply the nonlinearity and we obtain the signal at the next layer. And then we recursively add more and more of these layers, and maybe at the end we have an additional readout layer. And of course we have assumed that that x0 is the input signal. So we start with x. So it's just a recursive definition, a recursive application of graph perceptrons. As a shorthand notation for graph convolutional networks, GCNs, with L layers, we simply write that the prediction is f subscript calligraphic h, which now comprises all the coefficient vectors, one per layer, of x and the graph shift operator s, which is equal to the last element of this recursion, x big L, the last layer. And again, I mentioned this multiple times because it's important, the graph shift operator s is given is a prior information that they give to the model, and that is encoding the graph structure. So here's a block diagram of how this would work for a model with 3 layers. We have layer 1, 2, and 3. We input x, the signal, then we multiply that signal with this power series here with these coefficients h, 1k, and we get c that is pumped through this pointwise nonlinearity. So for each element of c, we apply element-wise separately to each element this sigmoid in this case. So we get x1, and then we do the same for x1, we get x2, we do the same for x2, and we get x3. You can see that s is always the same. In each layer, we're using the same power series, but the coefficients, they change. And the red coefficients here are the learnable parameters of this model. This is a graph convolutional network. More specifically, it's a graph convolutional network on signals where at each node we have a single real number, a scalar. Now, learning a graph convolutional network works the same as learning a graph filter. We again have the data set D, where we can have again different graphs for different elements of this data set. And then we have f calligraphic h of xs, the GZN with filter set h. And during training, we seek to minimize some loss function that measures the discrepancy between fh, the prediction, and y, the ground truth signal, output signal. And this optimization is over h, all filter coefficients. The graph shift operator is given as prior information, and the dataset may comprise multiple different graph instances. And empirically, and this is similar to MLPs, deeper GZNs work better due to this layered stacking of convolution and nonlinearities. And this is exactly the same as in CNNs, for instance, where you have also convolutions and nonlinearity stacked together. Now, as we mentioned before, graph convolutional networks are more flexible than CNNs, but they are less flexible than multilayer perceptrons, as they are a special case of multilayer perceptrons. If we consider a very simple form of a multilayer perceptron with a pointwise nonlinearity G, let's say a sigmoid, and ignoring the bias for now, we can define this recursively using this representation. Now, if we compare this to this, where we see the trainable parameters highlighted in red, we see that this model is more flexible because we can use this model to represent this model on the right. So this is a special case. The graph convolutional network is a special case of the multilayer perceptron. We also have a linear transformation, but in this case we have a projection onto this s to the power of k matrix, and then we have just a scalar coefficient h, while here we can learn an arbitrary matrix w that can be equivalent to this power series here, or it can be not. Now, as GZNs are a special case of MLPs, they attain a higher training cost. In other words, over the training set, and now in this case we are using the same S as the same graph and the same graph representation S for all the data points, because otherwise an MLP we couldn't execute on different graphs, because an MLP is not is by definition is not permutation equivariant as a graph convolution network is. So as these GCNs are a special case of MLPs, to perform like the training error that we see of an MLP, assuming that we have a good training algorithm, good enough training algorithm, is always smaller or equal than the training error of a GCN. Now this is maybe a little bit counterintuitive in the first moment, but the important thing here is that GCNs generalize better to unseen signals, as they are able to exploit internal symmetries of the graph signals encoded in the graph shift operator. By using the graph shift operator, which the MLP does not, the model may perform a little bit worse on the training set, but generalizes dramatically better to new signals on the same graph or to new graphs. And furthermore, the graph convolutional network is the only model in this comparison that can handle different graphs, where we can have an optimization during training time, and also at inference time we can apply this model to different graphs. We can do the convolution to different graphs because S informs the model about the structure of the graph. We're always projecting through S, so the dimensionality of X is linked to S and not to some generic globally trained parameter matrix W. So this is the beauty about graph convolutions. Here's a little illustration on the generalization properties. Assume the training examples are all similar, somewhat similar to this example signal shown here on the left. By the way, the signal strength is indicated here in terms of the strength of the blue color. So we have this strong signal at vertex 9 and a weaker signal at 10 and no signal at 5 and 6. Now an MLP would learn to predict signals that look like the middle signal rather correctly. But it's impossible if I have just training examples that look like this one to generalize to a signal here on the right. So the prediction, if this would be the input to the MLP at test time, if at training time I have only observed examples that look like these, is likely to be very bad. However, the GCN will succeed in this case as it knows the underlying structure of the graph. It basically performs convolution along the graph by knowing the structure of the graph. So it can infer that at node 6 in the input there's nearby nodes that have a strong activation. And so this pattern here is the same pattern as this pattern here, just it's occurring at different nodes in the graph. So there's this equivariance, the equivalent of the translation equivariance on convolutional neural networks we see here as the equivariance on the graph convolutions. What we've seen so far are graph convolution networks that are limited in the number of features at their input. In particular, we have assumed that the signal is one-dimensional. For every vertex in the graph, the input signal has one scalar. Now this is restricting both as an input but also as an intermediate representation. So we want to generalize this to allow for multiple features, to allow for vectors. Every vertex is now in a multi-input, multi-output GCN, and GCNS is in a multi-input, multi-output GCN is a feature vector. So we first define filter banks. Filter banks output a graph signal in a matrix form. So here we have a graph signal. This is a scalar per node in the graph. And the filter bank outputs a feature vector per node. So for instance, in this case, at node 6, we have 3 values in the output of this filter bank. How does it do that? Well, it's basically just applying 3 different filters independently on the input signal X. So we take the input signal X, we pump it through the first filter, we get C1. Through the second filter, we get C2, and then through the F filter, we get CF. So each of these C's here is a one-dimensional graph signal, where we have specified for each vertex one real number. But now we have F of them, so we have effectively specified a feature vector for each vertex. You can think of this as a book, where at each book page, like here, this is a book where at each page of the book we have specified a 1D signal, such that if we look at the entire book, we have a vector per node. This is a filter bank. Now, if we assume there's F input features per node, and we have a filter bank with G filters, then we process each input F with each filter G to yield outputs that are F times G. What this means is that this Mimo graph filter therefore generates an output with F times G features per node. So if we apply this over multiple layers, we have an exponential growth in the number of features per node, which is not desirable. Here we can see this. We have multiple input features per node, and then we have at the output we have, because we have multiple filters, we have this one dimension, and then we have multiple input features, the second dimension. So we have this F times G number of features per node. And in this illustration here, each of these U's is a graph signal where we have specified one scalar per node. So in this case here, we would have F times G scalars per node. Now the solution to this is simply summing over F. So we're summing these here over F to obtain exactly G features per node. And then we have an operation that maps from F features per node to G features per node. That is the summing here. Now this looks a little bit complicated, but we can, using matrix notation, using the beauty of linear algebra, write this in a very compact matrix notation. And this is the Mimo graph filter that you will see in many papers. And this can simply be written as a matrix C equals this sum, this polynomial over s to the power of k times the input x times the filter matrix hk, where the columns of C correspond to the G feature values and the row correspond to the n vertices. And then we have this n times n graph shift operator. And then we have a input signal that's n times f. So for every of these n nodes in the graph, we have f features. And then we have this feature matrix hk, which is f times g. So overall, we obtain n times g, a matrix of dimension n times g. And this is exactly equivalent to this formulation. Now, to define a Mimo GZN, a multi-input, multi-output GZN, we can recursively compose these L-Mimo filter layers as we did before for the standard GZN, where we had just one-dimensional features at every node in the graph. And we obtain this expression here, where again x0 is x, the input to the first layer, and this HLK matrices here are the parameters that we want to optimize over. And they specify in each layer from how many features we reduce or grow to how many features in the next layer. We can again write this in a more compact expression as the matrix prediction y is f calligraphic h of xs, which is the output of the last layer of this network, or the readout, where this calligraphic h is just a set of all of these matrices that occur in this computation. So it's this matrix H has two indices. It has index over the layers and over case. And the graph shift operator again is just occurring once and is given as prior information. It's the same over all the layers. So here we have a comparison of the first simpler GCN we saw and the Mimo GCN. You can see that the operations are almost the same, except that we have replaced the scalar h with a matrix h, and that the input and the output are now matrices and not vectors anymore. That's it. One concluding remark: we really just scratched the surface in this lecture. There's much more to graph neural networks, and there's separate entire lectures dedicated to this topic. And if you want to dive more into it, I can recommend this review on graph neural networks that reviews like the work that has been done in this area over the last 10 or 20 years. Thanks.